Yes.
Thank you very much. Sorry. So yeah, I'm going to talk a bit about interaction trees and verified compilation, notably about a case study on the verification of the Jasmine compiler we'll be working on in Sofia with Benjamin Gregoire. And yes, so first kind of bigger picture, we are essentially working on verified compilation, where there's been major projects going on using well-established semantics, well-established techniques, usually based on operational semantics, like small step semantics in the case of comp sets, which has generally the weakness of not being directly executable, or like big step semantics in the case of CakeML, which requires to deal with divergence using clocks and lower upper bounds. The technique that we're rely on now is interaction trees, which is basically, at least in the spirit, a denotational semantic technique. So it has the advantage of denotational semantics being compositional with respect to the language syntax, and also being executable in a way that's not exactly as straightforward as with standard denotational semantics, but we'll see that. It is basically a co-inductive technique, so it's okay with divergence. We don't need clocks, we don't need fuel. Computations are essentially represented as trees, as we'll see, and interpreted as monads, and trees themselves are monads, as a matter of fact. And additionally, they allow for the solved modularity, which is usually associated with free monads, and we'll see something of that as well. And the nice thing is that although they are based on co-induction, they tend to simplify reasoning by co-induction. First of all, relying on parameterized co-induction as an established technique in Roc to deal with co-induction more effectively, but also more specifically supporting equational reasoning. So basically allowing to do as a matter of fact, reasoning directly with co-induction usually comes with a significant cost, even if intuitively is quite nice. Just to give a bit of background, the very simplified views on interaction trees, they're basically just a co-inductive data type with three constructors. One, return the terminating computation that returns a value. One is a computation that advances by a silent step, a tau transition. And one is a computation that basically expects a visible event to be executed and to feed the return type to a continuation. Okay, so now this is the data structure that represents computations. And how do we interpret these computations? Well, the nice thing is that we can do it in a comparatively modular way using a representation of effects. Okay, so what I didn't say is that the data type, the representational computation depends on two parameters. One is the type family of events, E, and one is the return type that is going to be set in advance. So basically, the interpretation is comparatively modular with respect to the possible events, because we can consider subtype families of events and define event handlers which handle a specific family, a specific subfamily of events. The event handler is generally the basis for the definition of interpreter as a folding of the event handler on the tree, on the interaction tree. And in general, the definition of interpreter is generic in the sense that it's a definition that works with any handler. There are a few simplifications I've made here, but we'll mention them later. Now, this leads to a possibility to introduce a layered interpretation by dealing with each subfamily of events separately and then composing together the interpreters. So now, the object of our case study is basically an existing language, Jasmine, that's being developed at Sofia by Benjamin Gregoire and his team. And it's essentially a low-level language for cryptographic applications, which allows, which gives the programmer lots of control on the assembly which is generated. For example, it allows us to decide where a value is stored in a memory or in a variable or in a register and things like that. And it's used basically to implement and verify cryptographic protocols. As formalized in Rock, in Rock, and not only the semantics of language, but also the compiler, which is verified currently, well, at least in the past and up to now, using a semantics for terminating programs, essentially a big step semantics, unclocked. So only for terminating programs. We wanted to lift this restriction by switching to interaction trees. And up to now, we have verified the compiler with the new semantics for the front end, which is basically made of 20 passes, including constant propagation, data elimination, inlining, and stack allocation. So in a way, it's a comparatively easy compilation process because each pass is based on the same language syntactically, but the interpretation, the semantic interpretation changed after each pass depending on how data structures are interpreted in memory, essentially. Notwithstanding this, it has a concrete memory model, so unlike COMSA. So memory is always finite, as set by parameters in the beginning. Now, to verify a compiler, let's say this is also very simplified views. You have a source and a target program that you can relate, and basically what you're going to do is to produce a relation between states, and saying that for related input states, the semantics of the source is going to be related to the semantics of the target with respect to those input states. So this, in practice, means that you're going to, so if you execute the semantics on each side, you're going to end up either with states that are related or with non-terminating computations. Since we are working with deterministic semantics, there's no really great value added in distinguishing between forward and backward simulation. Still, there's difference between, if you want to look at it this way, between forward and backward reasoning, in the sense you can reason, you can make your proofs by induction on the source or on the target. We do it on the source. Okay, so Now, what does it mean to relate two programs? I want to relate source and target. So we can represent now our computations as trees. So basically, here you see, you have a relation that basically requires the two trees to differ only by a finite number of sudden transition steps, these tau steps. And for the rest, requires events to be exactly the same on both sides. And additionally, it allows you to match an error, a failure, with any terminating subtree on the other side. And of course, I mean, the condition that we've written there with K refers to the fact that we want co-inductively the continuations to be related. Okay, as you can actually see for the part of the tree that is shown, but it should be co-inductive, go throughout the whole of both trees. Now, this relation is very useful and very powerful in many ways, but it's also very constraining because it requires events to be exactly the same on both sides. And for example, there's a problem in our case because in the process of compilation, the function calls, which are events, change their type and change their input values. So basically, there are no more exactly the same events. There are ways to use this kind of relation to reason up to a point on the relation between two programs, and then allow for different interpretations, after which you won't be able to relate anymore the computations, but you'll still be able to relate the values. Or you can alternatively start from programs which have different events and basically interpret them down to programs which share exactly the same family of events. But nonetheless, it complicates a bit the style of reasoning you can make, especially if you have programs that are structurally quite similar, but not similar to the point of having exactly the same events on both sides. And also the other thing, we will read when we throw an error in the source, we don't want to worry about having something that terminates in the target, because in principle, we would like to associate an error with an undefined behavior in the standard sense. So basically, we a more permissive relation, which allows for events to be related but not the same on the two sides. And this capitalizes on stuff that's already in the I3 library, but it kind of gives a flavor to the verifications, which already oriented a bit towards whole logic, in the sense you have a phi parameter as a precondition between events that relates events, and a psi as a postcondition on the expected, as a relation on the expected values for the related events. And this time, you see, you can match an error with any subtree by declaring the error as what we call a cutoff. And basically, this is another feature or probably the novel feature that we added to relations that were already defined in the I3 library. Okay, so here, for example, here I'm showing not exactly the rock code, but the structure of the definition for this relation. So the first one I showed was equivalence up to tau. This was an equivalence up to cutoff in the sense that it takes into consideration these cutoff points. So, of course, there is the R relation between return values with return value types. And then we have phi as a precondition of event, psi as a postcondition on event execution. And then we have these CL and CR, which are predicates that decide which are the cutoff events, either on the left or on the right. We actually use just the cutoff on the left for error in the source. Okay, so basically this is an inductive co-inductive definition in the style of existing one that you can find in the I3 library. So basically the fact that the tau L and tau R rules use the premise inductively ensures that the two trees can only differ at most by a finite number of taus, okay? So you cannot relate in general a terminating tree with a non-terminating one, except for the case of cutoffs. Right, so the Jasmine semantics now is, so let's say the bigger, the main elements is a failure interpreter, which actually use a monad transformer to change the return type from V to an option. Actually, it's not an option; is a specific data type, but comparable to an option. And an interpreter, a recursive interpreter for function calls. And you get the interpretation, the modular interpretation, by composing together the two interpreters. And there could be more, okay? Now, here's a semantic excerpts from the Jasmine code, more or less. And you see here there's nothing really new with respect to existing semantics-based interaction trees. So here you can see the while loop. They use the iterator, the co-recursive iterator, which is provided by the I3 library. And you can see the function call event, which is triggered. And then it's going to be interpreted by the co-recursive interpreter. Right, so something about the modular verification in the sense of component-based verification. So basically, we say that we have a compiler that's front end that's made of about 20 passes. So each pass is verified separately, and the statement, the verification statement for each pass is basically a modification of the one we've seen before. So given the input state, given related input state, Si and Sj, then the source and the semantics of the source and the semantics of the target for these states is going to be related, this time by this equivalence up to tau, once we have set the variables appropriately. In particular, the CF means that the failure is a cutoff in the source, whereas the C null means that we have no cutoffs in the target. So we basically prove each of the statements which corresponds to verification of each compiler path by induction, by simple induction on the syntax of the source program. And then we compose them together by using the transitivity rule that we've proved for the relation. As a matter of fact, the verification use a kind of high-level relational whole logic, which I'm not showing here, but it's kind of, can be guessed by the implicit Hoare structure that's already part of the relation, of the equivalence relation that we've discussed. So now, what's the time?
26.
Okay. 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 Right. So we're going fast. So okay. Right. This already, in a way, shows what the transitivity rule for equivalence up to tau looks like in its full generality. As a matter of fact, we haven't used it in its full generality, but you see that we've got actually some constraints on the way the cutoff predicates are related with each other. Now, the nice thing, however, of this relation, and the fact that you have a possibility to introduce cutoffs on either side, is that it supports, in principle, both backward reasoning and forward reasoning, as well as backward simulation and forward simulation. And it, this kind of transitivity, for us is the basis to try to think to combine the two things together. Of course, I mean when you want to prove when you want to verify compiler, it's very important to preserve safety. So you don't want to introduce new errors in by the compilation process, but sometimes it can be convenient to introduce errors and then ensure later that these errors aren't possibly there by analyzing. So basically, in this sense, it can be possible to combine together forward and backward steps. At least that's something that we're considering. Now, the other things that it's interesting in our the one that I mentioned earlier about the fact that interaction trees support modularity. As a matter of fact, this modularity is more general in the sense that it comes with the possibility the return types using monotransformers. As a matter of fact, one could go one step further and say that the target of these interpreters might simply be monads, not necessarily I-trees. There are a few problems in the general, at least we found in our experience in using this approach. And of course, there's some problems with reasoning on the joint union modulo commutativity and associativity, this joint union of event families. And it's supported by kind of reasoning comparable to data type technique, comparable to data type a la carte, but there are still minor snags. And so the matching of interpreters is not generalized to more transformers, even if it is supported for specific molar transformers. And yeah, the painful thing is when you get to a point that, using the molar transformers library with some other libraries, maybe math-comp libraries and stuff, you get up with some universe inconsistencies that's rather hard to trace back to the source. And we've had a few problems there that now we've patched up in different ways, but that's basically some kind of limitation, let's say, in using this approach in a carefree way. But anyway, it's very, very good, very useful possibility. I mean, that of layering your interpreters as opposed to giving a single block semantics. So now, as a conclusion, what we've done so far, as I said, is the verification of the Jasmine compiler front end. And we've also formalized the probabilistic semantics of Jasmine. I'm not talking about that now, but using distribution monad from an extended real library. And what we want to do in the future is, of course, verify the back end, which includes linearization as the main pass. Also, we would like to compare our co-inductive I3 semantics with what you get out of fuel-based techniques, like those used for KML, in KML, for example, and step indexing, and yeah, in general, integration with safety analysis. So yeah, thank you for your attention.